This is Honors Algebra 2 Pre-Calc. We're doing 10.8 in Pre-Calc, which is polar graphing. So this entire video is going to be dedicated to the special polar graphs that you can see on page 760 of your textbook. I apologize in advance if I pronounce any of these wrong. I don't say these words all the time, but I'll do my best. Also, the graphs on page 760 are by far way better than mine. Not sure if you can see 760 clearly, but those graphs, way better than my graphs. So anyway. So let's start by walking through limacons. So limacons are of the form, here we go, a plus b cosine theta or a plus b sine theta, where a and b are both greater than 0. So they give us these 4 possible graphs. And again, you don't have to memorize these. I don't have them memorized. I've never had them memorized. It's fine. I think the ones most commonly that'll come up that you might want to have an idea of what they look like are the Rose curves, which we'll talk about in a sec. So you can have a limacon with a loop if a over b is smaller than 1, right? So basically saying if a is a smaller number than b, right? So you get this, and we actually saw this in one of our examples. We graphed one that was like this, I think in our example 2 maybe. So in this case, this is a cosine, and that's why it goes in this direction. If I picked one that was a sine, it would go up. We can have what's called a cardioid, which is like a heart shape, right? So it's actually got like a kind of a hard point that occurs right at the pole, and it looks like a heart. We can have what we call a dimpled limacon, which is sort of like the heart shape, but without the point, right? It's flatter, but still dimples in. And then we can have what we call a convex limacon, which just basically doesn't have that bend, doesn't have that dimple. And they all have different conditions for why they happen, right? So they specifically relate to the ratio between a and b, which again in the original equation, a was the constant and b was the coefficient of the trig function. You do not have to have these memorized, right? If you really want to look at the different images, I definitely suggest looking at page 760. You can also look at my really bad drawings. Let's talk about the Rose curve for a minute. So Rose curves. So they're the ones that have petals. We saw one of those when we did our last example. So a Rose curve has, so it's of the form a cosine n theta or a sine n theta, right? So the length of the petal is a, right? Sort of like the amplitude you'd see in a normal trig function, right? So a is the length of the petal. And then the number n tells you how many petals it has. If n is an even number, then it's going to have 2 n petals. So for instance, if this n in here were an 8, there would be 16 petals, right? If n is an odd number, then there are n petals. So if this n were, let's say, a 7, there would be 7 petals. And this is for n values that are greater than or equal to 2, because as we saw up here, if n were only, right, if n were only 1, then we'd end up with essentially, well, we didn't see it up here because this has a not equal to 0. We'll see it in a second when I draw you the next round of curves that include circles. But if n is 1, it's not a Rose curve. So, cool. So let's walk through the Rose curves. So the short answer is that the cosine curves have a petal that lies symmetric to the polar axis, right? So the cosine curve, so you can see right here, this petal, if drawn properly, would be symmetric to the polar axis, and so would this one. These are both cosine curves. So an example of a cosine with a 3 inside, like so cosine of 3 theta, would have 1, 2, 3 petals. Notice that the one petal is symmetric to the polar axis. An example of a cosine with 4 petals would have, or with 4 on the inside, so cosine 4 theta would have 8 petals, because remember, if n is even, it's 2 n petals. So 1, 2, 3, 4, 5, 6, 7, 8. But again, notice that because it's a cosine function, that first petal is going to be symmetric to the polar axis. For sine, there is not a petal symmetric to the polar axis. For sine, you'll find that the line of symmetry for the curve is going to be the, essentially, you're going to have a curve symmetric about the y-axis, or around theta equals pi over 2. So here's an example of a sine with 5 on the inside. So sine of 5 theta would have 5 petals. 1, 2, 3, 4, 5. Sine of 2 theta would have 4 petals, because remember, even numbers, you get double the number of petals. That's an example of the sine of 2 theta. The actual petals themselves are a units long. So this petal from the pole out to the end of the petal should be a units, and that would be true for every one of these petals, right? So it's a units, and they're all the same size petal. They don't always look the same when you graph them on a calculator because of that zoom square function, but that's kind of the idea. So let's talk about the last row on here. I couldn't fit it in easily, so I'm going to go ahead and put this on here. We're going to talk about circles and lemniscates, which for years I said wrong. I said lemniscates, but apparently it's lemniscates. So, you know, thanks, internet. So, circles and, Lemniscates. Okay, so essentially a circle is something of the form r equals a cosine theta or r equals a sine theta, and we've seen some of those. So if it's a cosine, this is r equals a cosine theta, it's going to be, it's going to have one of its, so it'll essentially have a diameter on the polar axis, right, with one of the endpoints of that diameter at the pole and the other one on the polar axis, and a will be the diameter, right? If it's a sine, the same thing will be true, but it'll be on the line theta equals pi over 2, right? So this would be r equals a sine theta, right? So those are both circles. Then lemniscates, so they're of the form, and they're slightly more complicated looking, but so r squared equals a squared sine of 2 theta, and r squared equals a squared cosine of 2 theta, and then they kind of look like an 8 or an hourglass. So they basically look like, sort of, I mean, the other argument is they're kind of like a degenerate rose curve, right? They kind of look like an 8 or an infinity or an hourglass. And in both of these cases, each of these two petals, right, which they're not really called petals, but their length is a, right? So again, that's all of the special polar graphs on page 760. You're definitely welcome to look at them. I certainly don't need you to memorize what they look like. Even when they refer to them on like a test, like on an AP test or something, they'll often give you a graph, or it'll be a calculator section where you can make your calculator graph.